Hi folks, welcome to 7.5 Trigonometric Form for Complex Numbers. So when we start this section, we're going to start by doing a little compare and contrast. So one thing that you might know, or you definitely know, is the Cartesian coordinate plane, okay? Sometimes this Cartesian coordinate plane is also called a rectangular coordinate plane, but they mean the same thing. Okay, they mean your basic XY plane. And so here I have an example of some points on an XY plane. So we've got 2, 4 over here. We've got -4, -3 over here. So we plot the X value first, and then we plot the Y value, okay? But let's scroll over here and take a look at the complex coordinate plane. So the complex coordinate plane is a little different because our two axes are not X and Y, but we have a real axis and we have an imaginary axis. And what that means is that all of the coordinates are going to have a real number first, like 5, and then it will be followed by an imaginary number or something with an I. Okay, and you'll notice that all of the points here follow that form. I've got an imaginary part, I've got a real part, and some of them it's a real part, but the imaginary part is 0, so we don't have to write that part, okay? But that's what a complex coordinate plane looks like, and we plot our points the same way, where we do the first number first, we go across, and then the second number tells us how far to go up and down. Okay, so now that we've established that, let's go back to a concept that you learned about Cartesian or coordinate planes, and that is finding the distance. And so what we're going to do is we're going to go ahead and use this point right here, okay? I know that's 2, 4, and I want to find out how far away that point is from the origin. In other words, I want to find this distance here. All right, so what we're going to do is I'm going to redraw that segment down below. All right, and this one has a coordinate of 0, 0, and 2, 4. And I'm going to draw the horizontal component. I'm going to draw that horizontal component, and then I'm going to go ahead and draw the vertical component. Now, if I want to find this distance, then I can do that by using the Pythagorean theorem. I know that my horizontal distance is 2, my vertical distance is 4, and so I can say a squared plus b squared will give me c squared. Or maybe I want to go ahead and solve for c right now. So I'm going to say c equals the square root of a squared plus b squared. And now I'm going to plug in my numbers. So the square root of 2 squared plus 4 squared. And that's going to give me the square root of 4 plus 16, or we can say the square root of 20. And that represents how far that point is from the origin. Well, it turns out that we can do something similar with distance on the complex coordinate plane. So I'm going to do the same thing. I'm going to pick a point, and then we're going to find that distance. So I'm going to pick this point up here, okay? So 2 plus 3i. And I want to find out how far it is from the origin. And so that means that I'm going to be finding that distance. So I'm going to go ahead and redraw that segment below like I did on the other side. So I've got my length I'm trying to find. I have a vertical distance and I have a horizontal distance. Now, in this case, the horizontal distance is 2 again, because it's 2 plus 3i. And the vertical distance is not 3i, but it's actually just 3. It's the coordinate in front of I. And I want to find out how long that side is. So I'm going to do the same thing. I'm going to pull from this part right here, already solved for c. And I'm going to say c equals the square root of a squared plus b squared. And so that equals the square root of 2 squared plus 3 squared, or the square root of 4 plus 9, or I could say that that distance is root 13. Okay, so we've shown that we can take stuff that we know about one kind of plane, the rectangular plane, and apply it to something that we are not quite as familiar with, which is the complex coordinate plane. So where does this take us? This takes us to the definition of absolute value in a complex number. So if you have a complex number, z equals a plus bi, then its absolute value is actually the distance. Okay, so this is the distance. That's what it represents. When we find that absolute value, we're finding how far that number is from the origin. Okay, so let's go ahead and take a look at something called trigonometric form of complex numbers. So the trigonometric form of complex numbers means that I can take something that might be on a complex plane and actually put it on a polar plane. All right, now we're going to learn about polar coordinates in chapter 10, I believe, in your textbook. So it's not something that we've learned yet, but just to kind of give you a quick preview, the polar coordinates look kind of like this circly bullseye business on the right-hand side. So I've got a bunch of circles and a bunch of angles, and when I write numbers in polar, I'm interested in the r and the theta. Okay, so when I'm thinking about polar, I want an r and a theta. And so, for example, if I had 2 comma pi over 4, that would mean I go to pi over 4, which is here along this line, and I go 2 circles out from the center. All right, so that's another way that we can kind of visualize points. And when you get to Calc 3, there's actually a lot of different ways to graph points. So we could do polar, we can do rectangular, we can do complex, and each one has its benefits. Each one allows us to compute certain things more simply. So where does that bring us to? The trigonometric or polar form for a complex number. So if z equals a plus bi, then r, that radius, is your distance from the center, right? That square root of a squared plus b squared. And our theta is an argument of z. That just means that our theta measures how far, what angle we go from the center, okay? Then we have something like this. Z can be written as r times cosine theta plus I sine theta, or very frequently we abbreviate it as r cis theta. Okay, so let's try a couple examples. Example 1, I want us to convert negative 4 plus 4i to trigonometric form. So what we're going to do is we're going to take this in 2 steps. The first step is we want to find our r. So find r. And we're going to find r by saying we know it's the square root of a squared plus b squared. So in this case, it is the square root of negative 4 squared plus 4 squared. Or we could say that that is the square root of 2 times 16, or we could say that it is 4 root 2. All right, so that's our first step. We're going to find our r. That gives us this piece of information. Now the only other piece of information we need is our theta. So that's going to be our second step. We're going to find our theta. And the formula that we have for that is we're going to do inverse tangent of b over a. And so if we do inverse tangent of b, which is 4, over a, which is negative 4, we will reduce that to arctangent of negative 1. Now remember, arctan of negative 1 means what angle has an x, or what angle has a y over x value of negative 1. And to help me answer that question, I'm actually going to sketch a quick picture of what that looks like, okay? So vertical, horizontal. So negative 4 plus 4i means I go 4 to the left and 4 up. All right, so the question is, what degree is that angle pointed in? And it turns out that that is pointed in 135 degrees, or more often than not, we use radians. So we're going to say 3 pi over 4. Okay, now our last step is just to plug everything into our formula. So z equals 4 root 2 cosine of 3 pi over 4 plus I sine 3 pi over 4, or we can write it like 4 root 2 cis 3 pi over 4. And that would be our answer. Okay, so let's try that again. Example 2, we're going to convert 2 plus 7i to trigonometric form. So we're going to start at the same place. I want us to find r. And so r equals the square root of a squared plus b squared. In this case, that is the square root of 2 squared plus 7 squared. Or I can say that that is the square root of 53. Second step, find theta. So to find theta, I'm going to use the function from above. So arctan of b over a. And that's going to give me arctan of 7 over 2. Now in this case, this is not a unit circle angle. Wow. A unit circle angle. And so because it's not a unit circle angle, we're just going to leave it like arctan of 7 over 2. And so we can write our final answer as z equals root 53 cis of arctan 7 over 2. Okay? So if it is a nice unit circle value, we want to simplify it like we did in 1, but if it's not a nice unit circle value, then we can just leave it in terms of the ratio of the sides. Okay, let's do one more example. So example 3, we're going to convert something that's in polar form to rectangular form. So here's how we're going to do that. We're just going to plug everything into our formula. So 12, I'm going to expand this out, cosine pi over 6 plus I sine pi over 6. I'm going to plug in my nice unit circle values. So cosine of pi over 6 is root 3 over 2, plus I sine of pi over 6 is 1/2. I'm going to distribute the 12, and I'm going to get 6 root 3 plus 6i. And that is our answer in rectangular form. All right, so that's where we're going to stop for part 1 of the video. Come on back for part 2.